Think about what makes us humans so, well, incredibly capable sometimes. Like you can walk into a brand new city, somewhere you've never been, right? And somehow you figure out how to get from point A to point B, maybe without even looking at a map first. Or, you find some gadget that's broken, never seen it before, and you fiddle with it, poke around, and maybe you even fix it. This kind of flexible, goal-directed thing we do, achieving new stuff without step-by-step instructions, it really feels like it comes from some kind of internal understanding of how things work, like a mental model we build.
That's exactly the intuition, isn't it? We're not just running on instinct or fixed reflexes. It feels like we carry around these rich internal pictures of the world around us. We can think, okay, what if I try this? And sort of run a little simulation in our heads about what's likely to happen. We can set these abstract goals like, I want to feel comfortable walking around this new city, or I need to get this machine working again. And then we use that internal understanding, that world model, to figure out a path, a sequence of actions to actually get there. It lets us plan proactively, explore possibilities mentally before we commit to doing something in the real world.
Right. This whole idea of an internal model, it feels absolutely fundamental to what we think of as intelligence, especially like general intelligence. And that just leads us straight into one of the really big, deep debates in AI, doesn't it? Is this kind of internal model, this world model, is it absolutely necessary for any system, AI included, to be truly general, flexible, goal-oriented across lots of different tasks? Or is there maybe a shortcut? Could an AI get super capable just by learning really sophisticated action-reaction patterns? Could it kind of bypass the incredibly difficult problem of building and maintaining this, huge, accurate model of our messy, complex world?
Yeah, that's really the core tension, philosophically and practically, in a lot of AI research. Can you actually get to general intelligence without having an explicit or maybe even an implicit representation of how the environment works? Can you just get there through observed behavior alone?
And that is exactly what brings us to the heart of this deep dive today. We're looking at a really interesting recent formal proof that dives right into this question. It kind of steps into this fundamental debate with some rigorous math, and it makes a really, really strong claim about what you need for general AI capability.
Exactly. This paper offers a formal answer. It demonstrates that for an agent, an AI, to reach a certain level of competence and multi-step goals, it must, just by necessity, have encoded somewhere inside its policy, its learned behavior, an accurate predictive model of its environment. The proof suggests there's no computationally cheaper shortcut to getting that kind of general ability.
Okay, so let's unpack this then. Our mission today is to really get into this proof, understand exactly what it's claiming, walk through the logic, and explore the really fascinating implications it has. Why, according to this research, isn't learning a world model just one way to build capable AI, but maybe an unavoidable and necessary step. So as you mentioned, this debate often gets framed as like model-based versus model-free AI. And we humans, we seem to use these world models almost without thinking about it. Like you navigating that new city. You're building a kind of spatial model, right? Understanding where things are relative to each other, how streets connect, potential shortcuts.
Totally. It's not just memorizing, okay, turn left here, then right at the light. It's more like understanding the bigger picture. Oh, the streets are mostly a grid, the river's over there to the west, the park is generally in that direction. And that model lets you recover if you miss a turn, or, adjust your route if you suddenly see a big construction site blocking the road. You can set a goal like get to the university library, even if you've never actually been there before, just by putting together bits of information and using your mental map to plan a route that seems plausible.
Right.
This whole proactive planning thing, thinking steps ahead, evaluating what might happen, that's classic model-based behavior.
And that's obviously been a huge inspiration for model-based AI systems.
Oh, absolutely. Model-based AI is fundamentally about trying to learn a representation of the environment's dynamics. How actions change the state of the world. If you have an accurate model, you can simulate future outcomes, which is incredibly powerful. You can use fancy techniques like Monte Carlo tree search. You see that a lot in game-playing AI like AlphaGo, where the agent basically simulates thousands, even millions of possible game paths using its internal model to figure out the best move. That's formal planning. And it's super valuable for tasks that need foresight or safety analysis, like predicting if an action might lead to a dangerous situation, or even just exploring possibilities without having to do costly trial and error in the real world, which means you can often learn faster with less data, better sample efficiency.
Okay, that sounds amazing. So why isn't all AI model-based then? What's the catch? Where's the difficulty?
The huge persistent catch is just how incredibly hard it is to learn accurate, general models of complex, real-world environments. I mean, think about it. How do you build a perfect model of fluid dynamics? Or the social interactions in a crowd? Or even just how a robot hand interacts with something squishy? The real world is messy. It's high-dimensional. Often things are probabilistic, not deterministic. It's usually only partially observable. You don't see everything. Environments change over time. There are hidden factors. The link between actions and outcomes can be super subtle and complicated. And ultimately, the performance of any model system is totally capped by how good its model is. If your model is flawed, your predictions are flawed, and any plans you make based on those predictions can just fail completely.
Right. So faced with that massive challenge, this other idea, the model-free approach, looked pretty tempting.
Precisely. The idea, which got a big boost from folks like Rodney Brooks back in the day with his intelligence without representation idea, was that maybe, just maybe, you didn't need to build this complex internal model of everything. Maybe intelligence could just emerge from simpler, more reactive behaviors. Systems that learn to map what they sense directly to what they do, states directly to actions, without that intermediate step of modeling the whole world.
Sort of like simple organisms, a bacterium moving towards food, or maybe a complex insect finding its way using learned reactions.
That was definitely part of the early inspiration. And look, model-free approaches have had absolutely spectacular successes recently, especially with deep reinforcement learning. We've seen AIs trained purely through trial and error, just optimizing some reward signal, conquer incredibly complex video games, control sophisticated robots, achieve top performance on all sorts of tasks. These systems learn policies directly, often from massive amounts of interaction data. And their success really seemed to suggest that maybe you could bypass that hard problem of explicit world modeling. Why bother modeling everything if you can just learn the right reaction for every situation you face?
And there's always a but, isn't there? The picture got a bit more nuanced. There's this growing feeling and some evidence that even these super successful model-free systems might actually be learning something that looks a lot like a world model, just implicitly, buried inside their complex neural networks, somehow encoded within the policies they learn.
That's the crucial observation that's really driving this recent theoretical work we're talking about. It's not like there's an explicit simulator programmed in or a separate box labeled world dynamics, but the patterns of connections, the computations happening inside a deep model-free agent's policy. They might, in effect, encode predictive information about the environment, simply because that information was necessary for the agent to learn the successful behaviors in the first place.
Okay, so the core tension is maybe sharper than ever. Is there a real model-free shortcut to general, flexible AI that avoids the pain of world modeling? Or is learning how the world works in some form just an unavoidable computational cost you have to pay for true capability, whether you do it explicitly or implicitly? And if it is unavoidable, how good does that learned model need to be? This paper tries to give a formal answer, at least in a simplified setup.
It does. And, to build a formal proof like this, you have to start by being really precise about the rules of the game and the players involved. They begin with a simplified environment model, what's called a controlled Markov process, or CMP.
Okay, CMP. Let's break that down for folks who maybe haven't spent their lives in RL theory. What does that mean?
Think of it as a way to mathematically describe an environment where what happens next only depends on where you are right now and what action you take. The past history doesn't matter directly. So it has a defined set of possible states, all the different situations the environment could be in. It has a set of possible actions the agent can choose from in any given state. And crucially, it has a transition function. This function, usually written PSA, tells you the probability of ending up in state S if you're currently in state S and you choose to take action A. And notice it's a probability taking action A in state S might not always lead to the exact same next state S. There can be chance involved.
Okay, so it's kind of like a board game. You have defined spaces, the ozzes, moves you can make, actions, and maybe like dice rolls or chance cards that affect where you land next, the probabilistic transitions. But the key thing is, where you land only depends on the square you're on right now and the move you just made, not what happened 3 turns ago.
Exactly. That's the Markovian property memoryless in a sense. And the controlled part just means the agent's actions actually influence these transitions. Now, for the proof to work cleanly, they make some standard assumptions about this CMP. Nothing too wild, but important. Like, it's finite dimensional, a limited number of states. It's irreducible, meaning you can eventually get from any state to any other state if you try long enough. It's stationary. The rules of the game, those transition probabilities, PS, don't change over time. And it has at least 2 actions available in each state, so the agent actually has a choice to make. These assumptions simplify the math, but still capture the core ideas of interacting with a dynamic, uncertain world.
Got it. Environment defined. Now, what about what the agent is actually trying to do, the goals?
Right, they needed a way to talk about diverse, multi-step goals formally, not just simple get to state X right now.
Hmm.
So they use a tool from formal logic called linear temporal logic, or LTL.
LTL. Okay, that sounds a little bit scary. How should we think about that without getting lost in symbols?
Yeah, don't worry too much about the formal syntax. The concept is the key thing. LTL is basically a language for describing properties of sequences of states unfolding over time. It lets you specify goals that have steps or things that need to be true for a while. They use a few core temporal operators intuitively, like eventually, usually shown as a diamond symbol, just means something has to happen at some point in the future. Next, often a circle means something must be true in the very next time step, and that just means something is true right now. Using these building blocks, they can define sequential goals, things like achieving sub-goal A, then sub-goal B, then sub-goal C in that specific order. The depth of the goal, which they call N, basically corresponds to how many steps or sub-goals are involved in the sequence.
Okay, so a depth 1 goal might be in the very next step be in state S. Simple. A depth 2 goal could be maybe next step be in state S, and then eventually after that, reach state T.
Exactly. And then, to capture the kind of flexibility we see in the real world, where there might be multiple ways to succeed, they define composite goals. These are basically logical OR statements connecting several sequential goals. The agent succeeds if it achieves any one of those alternative sequential goal paths. They use the symbol N, in EPSACN, to represent the set of all possible composite goals where each individual plan is a sequential goal with a depth up to N.
Okay, the maintenance robot example they use in the paper really helps here, I think.
Yeah, it's a good one to ground it. Imagine a robot whose main job is fixing problems. Its overall objective might be a composite goal like this. Either Plan A, successfully fix the broken machine, and that fixing process itself is a sequence of precise steps, a sequential goal. Or Plan B, find the nearest human engineer and tell them about the problem, which is another sequential goal involving maybe navigating, finding the person, communicating. The robot wins, achieves its overall goal if it successfully completes either Plan A or Plan B. This structure composite goals made up of sequential subgoals of potentially different lengths, up to depth N, that captures the kind of complex, flexible objectives we'd want a general AI to be able to handle.
Makes sense. So we have the environment, the CMP, we have these formal goals, LTL, composite sequential, max depth N. What about the agent itself? How do they define the player in this game?
They focus specifically on goal-conditioned agents. These are agents where the rule they use to pick their next action doesn't just depend on the current state, but also on the specific goal they're currently trying to achieve. So their policy, often written as pi, maps the current state, or maybe a history of recent states, and the current goal G to a specific action A. Just to keep the math cleaner for the proof, they usually assume the policy is deterministic for any given state and goal. The agent picks one definite action.
Oh, okay. And how do they measure if the agent is actually any good? Is it intelligent or capable?
Well, they could talk about optimal agents, agents that are absolutely perfect, maximizing the probability of achieving any given goal. But that's often unrealistic. Real agents aren't perfect. They learn from limited data. They have finite compute power. They're going to make mistakes. So the paper introduces a really crucial concept, the bounded goal-conditioned agent. This is laid out in their definition 5, and it's super important for the whole argument.
Ah, right. This is where they make an assumption about the agent's competence, not necessarily its perfection or rationality.
Exactly right. A bounded agent isn't necessarily optimal. It might not achieve the goal with the absolute maximum possible probability, but it is guaranteed to achieve any given goal, G, from that set N up to depth N, with a probability that's at least 1 times the probability that a truly optimal agent could achieve that same goal, G. You can think of delta as being like a failure rate or maybe a regret bound compared to the best possible performance.
Okay, so if delt was 0, the agent is optimal. If delt was 1, it could be totally useless, no better than random guessing maybe. So a small do means the agent is pretty good, its performance is close to the theoretical best for those goals up to depth M. A larger del, but still less than 1, means it can still achieve the goal reliably, just maybe not quite as efficiently or as often as a perfect agent could.
Exactly. And this definition is really powerful because it's purely about the agent's observable behavior, its actual competence on this defined set of tasks, composite goals up to depth N. It makes no assumptions about the agent's internal structure, how it learned, whether it's rational in some philosophical sense, or whether it's explicitly using a model inside. Just says, look, this agent can reliably get these kinds of multi-step jobs done with at least this level of success relative to optimal.
Okay, the stage is perfectly set. We've got the environment, CMP, the goals, LTL, composite, depth N, and the agent, goal conditioned with bounded competence up to depth N. Now for the really juicy part, the main theoretical finding. What does the theorem actually say?
Okay, the core result is Theorem 1, and it states pretty forcefully that any bounded goal-conditioned agent, the kind we just described, the one that satisfies that competence level 1 for goals of depth N, that agent must have learned a predictive model of the environment. Specifically, it must have learned the environment's transition function, PSSA.
It must have. That's a really strong claim, not just it probably has or it helps if it has. It's a necessity.
A mathematical necessity, yeah. Flowing directly from that definition of bounded competence for multi-step goals, N1. And the theorem actually goes a step further. It proves that this learned model is entirely determined by the agent's policy alone. All the information you would need to simulate how the environment behaves is already encoded, implicitly maybe, within the agent's learned behavior function, its policy.
Wow. Okay, hold on. So learning a policy that's good enough to achieve these diverse multi-step goals with some decent level of reliability, that's actually computationally equivalent to learning an accurate model of the environment itself. The information is fundamentally tied together.
That's the core argument, yes. The paper argues these two things, achieving that level of competence and learning the world model, are informationally equivalent. You simply cannot achieve that kind of flexible multi-step capability without somehow acquiring that predictive knowledge about how the world works.
Okay, how on earth do they prove that? How do you show that just being competent means you must have an extractable model inside your behavior? That sounds like the really clever bit.
It is clever. It's a proof by reduction, essentially. The overall strategy is assume you have an agent that meets the competence criteria, bounded, N1. Then design a procedure, they call it an extractor, that can figure out the environment's true transition probabilities, the PSA values, by only looking at the agent's external behavior, its policy. If you can show that this extractor always successfully recovers the true probabilities whenever the agent is competent, then it must be the case that the agent's competence implies that necessary information was present in its policy to begin with.
And this extractor works by kind of probing the agent, asking it questions in the form of specific goals.
Exactly. That's the intuition. The core idea, which they outline conceptually in their algorithm 1, is to craft very specific, carefully constructed composite goals. The extractor then presents these goals to the agent and observes the actions the agent chooses. The agent's choices between these carefully designed alternatives end up revealing information about its internal model of the environment's probabilities.
Okay, tell me more about these probing goals. How do they actually reveal the probabilities?
Okay, let's say the extractor wants to figure out one specific probability, PSA. That's the chance of landing in state S after being in state S and taking action A. First, the extractor needs a way to kind of steer the agent into state S and make it take action A. Let's assume it can do that. Then, right after the agent takes action A, the extractor presents it with a cleverly designed composite goal. This goal essentially forces the agent to make a bet on whether the outcome S occurred or not, or rather on the frequency of S occurring over many hypothetical trials. For instance, the composite goal might be structured like this. Achieve goal A OR, achieve goal B, where goal A is something like, eventually reach a state where if we hypothetically repeated this S then a process N times, the outcome S would happen at most R times. Goal B is the opposite. Eventually reach a state where if we hypothetically repeated this S then a process N times, the outcome S would happen more than R times.
Okay, wait. So you're giving the agent a choice that depends on the long-run frequency of a specific outcome landing in S, resulting from a specific action in a specific state.
Precisely. The trick is that these two goals, A and B, are designed to be sort of incompatible, or at least reflect different underlying beliefs about the probability PSA. Achieving goal A would be easier or more likely if you believe PSA is low, so getting at most R successes in N trials is likely. Achieving goal B would be easier or more likely if you believe PSA is high, so getting more than R successes is likely. Now here's the key. Because the agent is boundedly competent, remember, it achieves goals up to depth N, with a probability close to optimal its choice of action when presented with this goal A or R goal B scenario reveals information about its implicit estimate of PSA. A competent agent, to satisfy its performance bound, has to choose actions that favor the goal path that is actually more likely or achievable given the true underlying probabilities of the environment.
Ah, I think I see. Its choices are essentially forced to reflect the true probabilities because it's required to be good at achieving goals based on those probabilities. It can't consistently choose the wrong path, the one based on an inaccurate probability estimate, and still meet its competence guarantee. So by carefully changing the parameters R, the threshold number of successes, and N, the number of hypothetical trials, in these probing goals, the extractor can effectively narrow down the agent's implicit value for phi SA.
That's exactly the mechanism. The agent's policy, simply by virtue of being reliably successful within that bound year on these specially constructed tasks, is effectively forced to expose its internal model of the transition probabilities.
And the accuracy of the model you extract, that's tied to how competent the agent actually is.
Yes, absolutely critical point. The paper provides formal mathematical bounds on the error, the difference between the probability, the extractor estimates, and the true probability. This error is guaranteed to be bounded. And, crucially, that bound gets smaller, the extracted model gets more accurate as the agent's competence increases.
How so? In what ways?
Two main ways. First, as the failure rate approaches zero, meaning the agent gets closer and closer to perfectly optimal performance.
The extracted model gets more accurate.
Okay.
The better the agent is, the clearer its internal picture must be. Makes
Okay.
sense.
And second, as the maximum goal depth in that the agent can reliably handle increases.
The extracted model also gets more accurate. Why is that?
This is a really key finding. Think about planning over many steps. Even tiny errors in your estimate of the transition probabilities at each step can compound dramatically over a long sequence. If your internal model is even slightly off, your long-range predictions become wildly inaccurate very quickly, making it impossible to reliably achieve complex, long-horizon goals. So, to maintain that bounded level of competence for goals that require looking many steps ahead, high-end, the agent's underlying implicit model must be extremely close to the true dynamics of the environment.
Wow. Okay, so here's the really powerful implication then. For any level of competence whatsoever, any less than one, meaning the agent is doing better than just being totally useless, you can theoretically recover an arbitrarily accurate world model if that agent is capable of handling sufficiently deep goals, goals that require planning far ahead.
That's precisely what the error bound implies, because it depends on both one and, importantly, one N, or related terms. Long horizon capability, large N, forces the implicit learning of an accurate model, even if the agent isn't perfectly optimal in executing his plans based on that model. It's like, imagine trying to plan a cross-country road trip using a map that's fundamentally inaccurate about which cities are connected by which highways. You might be a fantastic driver, but if your map, your model, is wrong about the long-distance connections, you're just not going to reliably get to your destination. Your map, your model, absolutely has to be accurate enough for the length of the journey you're trying to undertake, high N.
They do mention a small caveat, though, right, about rare events.
Yeah, it's a practical point. The relative error in estimating the probability of very rare transitions might still be high, even for a competent agent. An agent might only need a highly accurate model of the common things that happen in the environment to perform well on most typical goals. It might get away with having a fuzzier understanding of very low probability outcomes. But if you then demand competence on tasks that specifically involve those rare events, the agent would likely need to refine its model of those rare transitions too, pushing the required accuracy even higher.
Okay, so Theorem 1 is the big one. Competence at multi-step goals, N1, forces the agent to learn an extractable world model. What about the flip side? What if the agent is only good at really short-term stuff? Immediate gratification, basically.
That's exactly what Theorem 2 addresses. It looks the edge case of what they call myopic agents. In the paper's definition, a myopic agent is one that is only capable of handling depth 1 goals, objectives that need to be achieved in the very next time step, and that's it.
Just optimizing for what happens right now, ignoring the future.
Pretty much. And the finding here is starkly different. For an optimal myopic agent, one that's perfect at achieving depth 1 goals, the information contained within its policy is not sufficient to determine any useful, non-trivial bounds on the environment's transition probabilities.
You can't extract the world model with any meaningful precision in that case.
Correct. If you tried to use their extraction method, the error bounds you'd get would essentially be trivial. They'd basically just tell you the probability is somewhere between 0 and 1, which you already knew. Useless.
Why?
Yeah.
What's different about only caring about the immediate next step? Why does that break the link?
Intuitively, think about what a purely myopic agent needs to know. To achieve a goal like be in state S in the next step, it doesn't actually need to know the full probability distribution, PSA. That is, the probability of transitioning to every single possible next state S after taking action A in state S. All it needs to figure out is which action A, when taken from the current state S, gives the highest probability of landing specifically in the one desired target state S for its depth 1 goal. The crucial point is that multiple, potentially very different, underlying probability distributions, PSA, could all lead to the same conclusion about which single action A is the best one for maximizing the chance of hitting that specific S next. The myopic agent's policy only needs to encode that best immediate action. It doesn't need to encode the probabilities of all the other possible outcomes that didn't happen to be the goal.
Ah, okay. So if my only goal is to step onto the specific square right next to me, I don't need to know the exact probabilities of ending up on 5 other different squares if I choose to move forward. I just need to know that moving forward gives me the best chance of landing on that one target square. The other possibilities are irrelevant to my immediate goal.
That's a perfect way to put it. The information about the full dynamics, the probabilities of all the successor states S, simply isn't required for a purely myopic agent to be optimal at depth 1 tasks. Therefore, that information isn't guaranteed to be encoded in its policy in an extractable way. So the conclusion from Theorem 2 is that world models become computationally necessary, according to this proof, specifically when agents need to deal with goals involving multiple steps, sequences, or choices between sequences. And 1. Myopia might allow a shortcut around full world modeling. General long horizon capability apparently does not.
Okay, so the theory is compelling. Long horizon competence implies an extractable world model. Did they actually try this out? Did they test if you can really pull models out of agents using this kind of probing method in practice?
Yes, they did. Section 3.1 in the paper covers their experimental results. They implemented versions of their model extraction algorithms, specifically a slightly simplified one they call Algorithm 2, and tested them on actual agents that they trained in simulated environments.
And what was the experimental setup like?
Pretty much mirrored the theoretical setting. They created agents trained using standard reinforcement learning techniques on experience trajectories collected within randomly generated finite CMP environments. They deliberately vary the amount of training data and aspects of the training process to produce agents with different levels of competence specifically, agents that could reliably handle goals up to different maximum depths.
And what did the experiments find? Did the extraction actually work on these trained agents?
Yes, they found that the extraction procedure generally worked well in practice. Interestingly, even when the agents they trained weren't perfectly boundedly rational, in the strictest theoretical sense, like a real agent might meet the A bound for most goals, but completely fail on a few tricky ones. Even then, the algorithm was still able to recover the true underlying world model, the PSA values, with reasonably low average error across all the different states and actions.
So the strict worst-case theoretical requirement might be a bit pessimistic, and in practice, the average performance is often better.
That seems to be what their experiments suggested, yeah. And the most critical finding, they clearly observed that the average error in the extracted world model consistently decreased as the maximum goal depth and that the trained agent could successfully handle increased. And the way this error decreased as n grew actually scaled similarly to what the theoretical bounds predicted, roughly like 0.12, meaning the error shrinks as n gets bigger.
O and 12. Okay, so the error definitely goes down as the agent gets better at longer tasks, even if the improvement slows down a bit for very large aeration. But still, it confirms empirically that this link between long horizon capability and the accuracy of the implicit model holds up.
Exactly. The experiments provided solid empirical backing for the core theoretical claim. The ability to handle increasingly deep, complex goals seems strongly correlated with the accuracy of the implicit world model embedded within the agent's policy, and crucially, that model can be recovered, at least approximately. And this connection holds even under more realistic training conditions where agents might not perfectly meet the strict theoretical competence definition for every single possible goal.
Okay, so the proof seems solid within its defined boundaries, and the experiments give it some practical legs. This feels like more than just a theoretical curiosity. It must have some pretty significant implications for how we think about AI research and maybe even beyond. Let's really dig into the so what now.
Yeah, absolutely. I think the most immediate and maybe most significant implication is that it makes a very strong argument against the idea of a simple model-free shortcut to achieving general artificial intelligence.
Meaning you can't just like train a bigger and bigger neural network on more and more data using standard reinforcement learning and just hope that general flexible intelligence will magically pop out
Yeah.
without that system somehow, somewhere, learning how the world actually works.
Not if you want that agent to be reliably competent at achieving a wide variety of multi-step goals in different situations. That's what the result implies. For agents to have general capabilities, the kind of adaptability and flexibility we associate with human intelligence, this work suggests the computational challenge of learning an accurate world model is essentially unavoidable. It's a prerequisite for handling diverse, long-horizon tasks. And that really reframes the core difficulty in building AGI. It's not just about learning a complex mapping from inputs to outputs. It's fundamentally about learning the underlying dynamics that govern how states change over time due to actions. This could lend significant theoretical weight back to research on model-based architectures, the ones that directly try to learn and use explicit world models, because this proof says that challenge is necessary anyway.
It also seems to connect really nicely with this whole idea of emergent capabilities that we hear so much about with very large models like LLMs.
It really does. It provides some potential theoretical grounding for why that might happen. The paper supports the hypothesis that abilities that seem to just emerge in these massive models, things like reasoning, or maybe even basic physics understanding in language models, might arise precisely because the training process itself forces them to learn an implicit world model. Even if the training tasks seem simple on the surface, like predicting the next word, performing well across a vast and diverse range of such tasks might require understanding sequences, consequences, relationships essentially, learning a model of the world represented by the data. And the fact that the proof shows competence is only needed on a subset of possible goals within Denon is really interesting here. It suggests that mastering even a relatively limited set of structured multi-step tasks could provide enough pressure to compel the agent to learn the general dynamics of its environment.
Wow, so an agent trained on what look like fairly simple tasks might suddenly unlock the ability to do much more complex, novel things, simply because solving the simple tasks forced it to build a general world model along the way. That's a powerful idea about generalization.
It suggests generalization might be driven more by the quality of the underlying learned model than just the sheer number of different tasks seen during training. And the paper takes this idea even further, speculating about how it might help explain complex human cognitive abilities. They argue that many things we consider hallmarks of human intelligence, adapting to new situations, reasoning under uncertainty, understanding social cues, causal reasoning, thinking counterfactually, what if I'd done that differently? Imagination, figuring out others' intentions, all seem to rely heavily on having a rich internal world model.
And this theorem offers a potentially simple evolutionary or developmental story for how those sophisticated abilities could have emerged.
That's the suggestion. The core evolutionary pressure might not have needed to be something incredibly complex like navigating intricate social hierarchies or dealing with extreme resource scarcity, as some theories propose. According to this result, maybe the pressure just to perform basic goal-directed tasks that require looking a few steps ahead, like navigating to find food or figuring out how to use a simple tool, could have been enough to drive the initial development of world models in our ancestors. And once those basic world models were in place, they would provide the necessary computational foundation for all those more advanced cognitive abilities to be built upon later. Achieving even simple multi-step competence in one necessitates the core building block, the world model, which then enables a whole cascade of higher-level capabilities.
That's a fascinating thought that the roots of really complex human thought might lie in the basic computational demands of surprisingly simple actions.
It's the implication they draw from the formal necessity of world models for achieving even bounded competence at multi-step tasks, at least in this simplified mathematical setting.
Okay, let's switch gears a bit. AI safety. This is obviously a huge topic right now, especially as AI gets more powerful and potentially more general. How does this proof connect to safety and maybe interpretability?
This is where the extractability part of Theorem 1 becomes really relevant, potentially quite important for safety discussions. Many proposed techniques for ensuring AI safety and alignment, things like understanding what the AI will do, predicting its behavior, maybe intervening if it's about to do something harmful, often rely on having an accurate predictive model of both the agent's policy and the environment it's operating in. A major worry is the black box problem, right? These complex AI systems, especially model-free ones, can become incredibly capable, but we might not fully understand how they work or why they make certain decisions. The concern is that their capabilities could outpace our ability to model, predict, or control their behavior, especially in new or complex situations.
Right. We worry about creating powerful agents whose actions we can't reliably anticipate or interpret.
Exactly. This paper offers a theoretical counterargument, or perhaps a source of hope, against that starkest version of the black box problem. It provides a theoretical guarantee that from any sufficiently capable agent, one that's competent at long-horizon goals, meeting the E1N1 criteria, we can theoretically extract an accurate world model directly from its policy. And here's the kicker. The more capable the agent becomes at complex, multi-step planning and execution, higher and low and lower A, the more accurate the world model we can theoretically extract becomes.
That seems incredibly significant because the safety concerns arguably become most acute precisely when agents become highly capable and can plan effectively far into the future. And the theorem says it's exactly at that point that their implicit understanding of the world, their model, becomes potentially more accurate and more accessible to us.
It suggests a possible pathway towards understanding and auditing little powerful systems. If the information needed to simulate the environment is necessarily baked into the policy of any capable agent, then perhaps we can develop scalable practical tools building on their theoretical extractor algorithm to actually pull that information out and inspect it. This could allow us to audit an agent's understanding of the world, maybe identify potentially dangerous misconceptions or biases baked into its implicit model, and predict its future behavior more reliably. It also lends some theoretical support to ideas about focusing on developing safer Oracle AI systems that are very good at prediction, but maybe don't take actions themselves, because the paper shows the capability to predict accurately is inherent in the capability to act competently over the long term.
So instead of just this inscrutable black box whose inner workings are a total mystery, a truly capable future AI might, in a way, be more like a glass box, at least in the sense that its effective understanding of the world, encoded in its behavior, is theoretically knowable by us.
That's the exciting theoretical possibility that the extractability result raises, yes. Of course, the huge practical challenge remains, developing algorithms that can actually perform this model extraction efficiently and accurately on the kind of massive, complex neural networks used in state-of-the-art AI today. That's non-trivial.
Does this result also suggest any fundamental limits on what AI might be able to achieve?
Oh, absolutely. It cuts both ways. If achieving truly general, capable AI performance in the real messy world requires learning an accurate model of that world, then the inherent, undeniable difficulty of accurately modeling the real world itself seems to place a fundamental bound on how capable AI can ultimately become, at least in terms of guaranteed reliable performance across arbitrary tasks.
Because the real world is just fundamentally too complex, too dynamic, too unpredictable to ever model perfectly.
Precisely. Real-world environments are incredibly high-dimensional. We only ever partially observe them. They're constantly changing, non-stationary, full of unpredictable events and hidden factors. Our ability, or any agent's ability, to learn a perfectly accurate general model of that kind of environment is fundamentally limited by things like the amount of data available, computational constraints, the sheer complexity, the curse of dimensionality. Therefore, according to this logic, an agent's capacity for robust generalization and reliable performance across truly novel situations in the real world is ultimately constrained by how well it can actually learn the true dynamics of that world. In domains where learning a truly accurate, comprehensive model is effectively impossible due to the inherent nature of the environment itself. Well then, achieving guaranteed general competence, satisfying that non-trivial regret-bound one for arbitrary long-horizon tasks, might be fundamentally impossible without relying heavily on continuous, potentially slow, online learning and adaptation forever.
Huh. So the dream of maybe training some massive AI offline once and then deploying it to be arbitrarily capable and reliable in the wild, messy real world, that might hit an inherent ceiling, simply because it could never learn a perfect enough model of that world from any finite amount of training data.
That's one possible interpretation of the limits implied by the necessity of world modeling, yeah. And remember, this proof is already set in simplified, fully observed Markovian environments. The limitations on capability tied to the difficulty of learning the model would likely be even more severe in realistic settings that are partially observed and non-Markovian.
It's probably also important to touch on the paper's own acknowledged limitations. What are the authors careful not to claim they've proven?
Yes, they're quite clear about the boundaries. As we just mentioned, the proof is formally constructed for fully observed environments. The real world is often only partially observed. There are hidden states, things you can't directly see. The proof doesn't necessarily say what an agent would need to learn about those hidden factors to achieve the same kind of flexibility. That's an open question.
And they also emphasize, right, that the proof shows the model exists implicitly within the policy's information content. It doesn't claim that the agent necessarily uses that model internally in a specific way, like consciously running simulations in its head for planning.
Correct. They are very careful not to make strong claims about the agent's internal cognitive architecture or subjective experience. It's not a proof about agent knowledge or consciousness or anything like that. It's a statement about the information that must be present in the learned policy specifically, that it has to contain enough information to reconstruct the true environmental dynamics, regardless of how the agent actually learned that policy or how it internally computes its actions.
Okay, stepping back a bit, how does this work fit in with or maybe differ from other related concepts in AI theory? They mention things like inverse reinforcement learning and mechanistic interpretability in the paper.
Yeah, those are important connections to understand. The paper positions its main result within a kind of logical triangle, which they illustrate nicely in their figure 1. It connects three fundamental problems in AI. First, there's planning. If you're given the world model and you're given the goal, how do you find the best policy, the best way to act? That's standard RL. Second, there's inverse reinforcement learning, IRL. If you observe an agent's policy, how it acts, and you're given the world model, can you figure out what the agent's goal or reward function must have been? And third, this paper's contribution. If you know the agent's goal or class of goals it can handle, and you observe its competent policy, meeting the regret bound, can you extract the underlying world model? Ah, okay. So planning is model plus goal gives you policy. IRL is policy plus model gives you goal. Yeah. And this paper is essentially policy plus goal gives you model. It kind of completes the triangle. Exactly. It adds a new vertex and edge to this theoretical framework, showing a fundamental relationship between these core components of goal-directed intelligent behavior.
What about mechanistic interpretability, or MI? That whole field is also about trying to peek inside the black box of AI models and figure out what they've learned. How does this relate?
There's definitely a shared goal there, understanding the implicit models or representations learned by AI systems. But the approach is quite different. MI typically focuses on probing the internal workings of a specific neural network, looking at neuron activations, connection weights, trying to identify specific circuits or features that correspond to learned concepts or potentially implicit models.
Right. MI tries to look inside the specific implementation of the black box.
Exactly. This paper's result, in contrast, is about extracting the model purely from the external policy, just from the agent's observable input-output behavior, mapping states and goals to actions. Crucially, it doesn't require any access to the agent's internal architecture, its weights, or how it was trained. This is a much weaker and therefore more general access assumption. It means the result, and the theoretical extraction method applies universally to any system that exhibits the required level of behavioral competence, regardless of whether it's a neural net, a decision tree, or something else entirely. It ties the existence of the extractable world model directly to the agent's capability, its performance bound on goals of depth and merit, not to the specifics of its internal implementation.
Okay, so MI might find a model-like structure inside a particular network architecture, but this paper proves that for any system demonstrating a certain level of general competence, a model reflecting the true environmental dynamics must be implicitly present within its overall behavior, its policy, regardless of how that behavior is generated internally.
That's a good way to summarize the distinction. Also, their proposed extraction method, algorithm 1, is in principle unsupervised at the time. It just probes the policy. Many MI techniques often require some form of supervision or prior knowledge about what internal features to look for, although they do mention that while their main result is about recovering the true dynamics, a slight tweak to the assumptions could potentially allow their method to extract the agent's subjective model of the world, even if that subjective model is flawed or incomplete.
Interesting. They also briefly touch on this idea of an agential causal hierarchy. What's that about?
That's connecting to some related work, suggesting that different kinds of generalization might require different depths of world understanding. The idea is that needing a predictive model, like the one proven necessary here for task generalization, handling varied goals within the same environment, is perhaps less demanding than needing a full causal model. A causal model, which understands not just correlations but underlying cause and effect mechanisms, might be necessary for more robust domain generalization, adapting effectively to entirely new environments where the underlying rules or causal structures might be different. So this paper's result solidifies the theoretical requirement for at least the predictive level of world modeling as a prerequisite for flexible task generalization.
And they explicitly link this back to practical AI research happening now, like work on agents conditioned on goals specified in LTL?
Yes, exactly. Because researchers are actively building and training agents designed to generalize, sometimes even zero-shot or few-shot, to new goals given in formats like LTL instructions. This paper's theoretical framework aligns directly with those kinds of practical efforts. It suggests that the formal results, and maybe even practical versions of their extraction algorithm, could potentially be used to analyze, understand, or even debug the implicit world models that these real-world goal-conditioned agents are learning.
Lastly, they draw a distinction between their work and classical representation theorems. What's the difference there?
Yeah, that's an important nuance in the theoretical landscape. Classic representation theorems from economists and decision theorists like Savage are really interesting. They show that if an agent's choices consistently satisfy certain axioms of rationality, like preferring A over B and B over C implies preferring A over C, then you can mathematically describe that agent's behavior as if it were maximizing some internal utility function based on some subjective probability distribution, a model, over possible world states. These theorems essentially show that you can fit a subjective model and utility function to the observed preferences of a rational agent.
Okay, so those theorems say rational agents act like they have a model and consistent preferences.
Exactly. But here's the catch, as the paper points out. You can mathematically fit some subjective model and utility function to almost any policy, even a policy that just chooses actions randomly. That doesn't prove that learning or having a model was necessary to generate the behavior in the first place. This paper's result is fundamentally different. It does not start with assumptions about the agent's internal rationality or decision-making process. Instead, it starts with an assumption about the agent's external behavioral competence specifically, its ability to reliably succeed within bound-up at multi-step goals, depth and one. And from that competence assumption, it proves that the agent's policy necessarily implies sufficient information to reconstruct the true environmental dynamics, PSA. It's about the information required for competence, not about fitting a model to choices assumed to be rational. And Theorem 2 reinforces this, showing the necessity breaks down for myopic agents, which are often the focus of those classical analyses.
It almost feels like this paper provides a kind of foundational argument that could support other approaches, like active inference, or maybe some theories of consciousness, which often start by assuming agents have world models.
Yes, I think the authors see it that way too. They view their results as offering strong theoretical backing for frameworks that posit world models as central to intelligent behavior. But instead of just assuming world models exist because they seem useful, this work attempts to show that assuming a certain level of behavioral competence logically implies the existence and potential extractability of those models. That could be seen as a more empirically grounded starting point for building theories about intelligence.
Okay, so let's try to wrap this all up. What's the absolute core thesis, the main conclusion the authors really want us to walk away with from this deep dive?
Well, conceptually, they connect it back to some really old philosophical ideas. This notion that the structure of an intelligent agent must somehow mirror or reflect the structure of the world it lives in. The old man as a microcosm sort of idea. They wanted to put some formal mathematical meat on those bones, specifically for AI.
And the proofs is their way of doing that.
Exactly. They proved, within their formal setting, that any agent capable of generalizing effectively across a sufficiently rich set of simple, multi-step goal-directed tasks specifically, achieving that bounded competence on composite LTL goals of depth greater than one, must have implicitly learned an accurate predictive model of its environment's dynamics. The information required to simulate how the environment behaves is necessarily contained within that agent's learned policy, its pattern of behavior.
So the big takeaway, for truly general AI agents, learning a world model isn't really an optional extra or just one possible technique. It's a necessary computational price of admission.
That's the strong final message, yes. Efforts aimed at creating truly general AI cannot realistically hope to find a clever shortcut that completely sidesteps the fundamental challenge of world modeling. And instead of seeing world modeling as this intractable problem we should try to avoid at all costs, they argue we should actually embrace it, because tackling that challenge head-on seems necessary for achieving advanced capabilities, and importantly, it might also be the key to making progress on critical issues like AI safety and interpretability.
And they point towards some really interesting directions for future research based on this, right? Like exploring different kinds of goals, maybe finding the absolute minimal set of tasks that are sufficient to force an agent to learn a general world model, developing practical, scalable algorithms to actually extract these implicit models from huge neural nets, and maybe even using this proven link between how well a model can be learned and how capable an agent can be to derive fundamental theoretical limits on AI performance in really complex real-world domains.
Yeah, they really see this as reinforcing the importance of research into understanding what's going on inside the AI black box. Because, according to their result, for truly capable agents, that inside must contain a reflection of the world outside a reflection that we can, at least in principle, decipher and understand.
Okay, this has been a seriously deep dive into what feels like a really foundational result. Thinking about this core idea that an AI's learned pattern of behavior, its policy, has to contain enough information to simulate its entire environment just because it's good at multi-step tasks. I mean, what does that tell us about the nature of learned intelligence itself?
It really makes you wonder, doesn't it? It suggests that maybe achieving true mastery over an environment isn't just about learning the right sequence of actions. Maybe it inevitably involves building, whether explicitly or implicitly, some kind of runnable mirror of that environment inside the agent itself. The ability to act effectively emerges from the ability to predict effectively.
And what new possibilities, or maybe even responsibilities, does that create for us? If competence implies extractability, like the theorem suggests, does that give us a fundamental lever, a way to potentially understand and audit even super capable future AIs, precisely when their safety questions become most critical? But then, on the flip side, that same link implies that the sheer difficulty of truly modeling our incredibly complex world might put a natural brake, maybe even a hard wall, on just how general and reliably capable artificial intelligence can ever become without constant, expensive interaction with the real thing.
Definitely a lot to chew on there.
Absolutely. Well, that's it for this deep dive. We hope you feel maybe a little bit more informed and perhaps a lot more curious about this deep, deep connection between being capable and understanding the world.